In this video, we'll be taking a look at phase lag on an aluminum plate using a differential surface probe. And we're first going to demonstrate the calibration just using some EDM notches. Where my left hand finger is here, we got the 3 EDM notches. And then the actual sample we're going to look at has just some small diameter flat bottom holes. I have my Workstation 2000 here set up for dual frequency, 800 kilohertz on the left, 200 kilohertz on the right to show the differences in phase when we encounter certain flaws. Now this probe that I have in my right hand is a differential arrangement, self-comparison differential. Now there's a little line on the probe right here, and you have to have that facing the direction of probe travel. So you have to keep the probe orientation correct so you have the right angle of attack as you approach each flaw. All right, so I'm just going to place my coil down on the material. Now this is differential again, so setting noise horizontal is probably not the best approach, but I just pretended like how would I set up with bobbin. And I set a flaw, in this case the 50 mil deep flaw. I set that around, I don't know, 15 degrees, something like that. You know, if I'm writing the procedure, I can dictate how I want to set my rotation. And in this case, 50 mil EDM notch to about 20 degrees. So for the purpose of this demonstration, that's going to work fine. All right, let's move over to our cal block. This is about an 1/8 inch thick of aluminum. And all I did to make this was I got a pretty small drill bit, maybe 3 millimeters across. And I went in from one side and just drilled the shallowest hole I could. Then I got progressively deeper until I got to the far end where I would go through wall. And I actually did that. I did 3 rows of those. And then I covered each row of flat bottom holes with aluminum foil. First with 1 sheet of foil. In the middle here, we've got 2 sheets of foil. And then in the last end here, we got 3 sheets of foil. So we're going to be looking at flat bottom holes of varying depths, just below the surface, a little bit more below the surface, and then 3 sheets of foil below the surface. And I don't know exactly how this is going to turn out, so let's just start scanning some of the flat bottom holes. So I got to figure out which end is my shallow end. So the side towards me is going to be only 1 sheet of aluminum. So I'm going to start scanning along. We're going to come to the first little pit. So yeah, this is just below the surface and it's not very deep. But look at which channel has more phase lag. It's the one on the left. That's 800 kilohertz. Because, you know, an eddy current system is basically using the coil to survey the test material. And it's basically giving a report back to the instrument of what's happening at every depth. So because it takes longer for higher frequencies to penetrate through the material and get the report back to the test system, it's going to have more phase lag. It takes longer to send and receive information on the higher frequencies. All right, the frequency on the left there is 200 kilohertz, and that has just about no phase lag for this very shallow pit just below the surface. So now we're going to get to one that's a little bit deeper, and just notice that channel 800 kilohertz on the left has more phase lag. And then I'm just going to go across the next deepest one, next deepest, and you're going to always see that, you know, the frequency on the right has very little phase lag because it's 200 kilohertz and it's a lot more, penetrates deeper quicker than the 800 kilohertz. All right, we're getting almost to the end. See, don't you like that differential signal for a little tiny surface probe? I mean, who is going to miss those flaws? Nobody, hopefully. And they have a very distinctive look, right? The dual polarity differential signals. You wish every probe could have those. Well, they don't. All right, so now we're going to go down to the, this is going to be our 2 layers thick of aluminum foil. We're going to see how much difference that makes on our phase lag. I'm just scanning across all the way. Yeah, you can see with 800 kilohertz on the left, those phase angles are quite a bit higher. I'll go back to the first row. Look at the phase angles, first row. Now I'm going to go to the second row. Look at the phase angles for 800 kilohertz. You can tell they're steeper. It's because this is under 2 layers of aluminum foil, so they're deeper subsurface flaws. Now we're going to go to the final. This is the layer with 3 thicknesses of foil on the top. Let's see what it does to those phase angles for the 800. I got to find the row. Where are they at? Right here? Right about there. Not only is the phase angle maybe a little bit higher, the amplitude of the flaws are getting smaller because they're farther below the surface. Eddy currents farther below the surface are less dense than the eddy currents at the surface of the material. When they're less dense, they have less weighted average input to your system output. I'm just scanning back and forth across those. Well, what's that doing on the 200 kilohertz on the right? Well, there's a lot more phase lag than there was with only 1 sheet of foil. So concentrate on the Delisiju on the right. I'm going to quickly shift back to the 1 layer of aluminum foil. I see the signals on the right. They're laying pretty flat. What are they, 10 degrees, 15 degrees? But when I go 3 layers deep of aluminum foil, you can see that the phase is kicking up a little bit. Let me just find one nice pit here to focus on. Okay, this is 3 layers deep. Look at the one on the right. 3 layers deep, and then I'm going to go back to the original. There's one right there. So what's that, like 5 degrees? But then when I go 3 layers deep, now we've got like 30 degrees. So here you can clearly see that there's phase lag difference between 2 different frequencies, and also that phase lag is going to increase the deeper you go in the material subsurface. I can tell by doing this demonstration on a 2-frequency tester, it's going to be a little more interesting to see it on the MIS 27, because on that instrument, we got all the cool colors and we can look at 4 frequencies at once. So stay tuned. That'll be the next video. End of lesson.